Hi, this is Inhwan Bae. In this video, I'm introducing a brand new crowd behavior generation task, taking a step beyond the traditional trajectory prediction methods. Crowd modeling, or crowd simulation, is widely used across various fields. In particular, generating and compositing virtual crowds is a common technique to enhance the realism and immersion of movies and video games. Crowd simulation is also essential for autonomous driving and urban planning to make virtual world or synthetic scenarios to help evaluating crowd safety and optimize designs. To synthesize virtual crowds, most companies use rule-based simulation software. Workers randomly position virtual agents and manually set up handcrafted rules to make them work on. This process requires a huge amount of manual work, often taking months of work just to produce a few seconds of footage. There are several approaches to try to transform it into a loadable task. In detail, the trajectory prediction task forecasts fixed length future trajectories based on historical trajectories, whereas traffic scene generation task places vehicles on maps and then predicts short-term future trajectories. However, these tasks remain insufficient as a crowd model due to their numerous operational constraints. To effectively model crowds, a new task is needed that covers lifelike behaviors. Let's look at a real-world scenario. From a bird's-eye view, people continuously enter from entrances and work toward their destinations. While working to the destination, they naturally do various behaviors like stopping to chat, joining groups, working together, and avoiding collisions. To simulate this natural complexity, we introduced a new task called crowd behavior generation. This challenging task is designed to overcome the constraints and limitations of previous tasks. Specifically, given an implicit image, the generative model predicts an infinitely long sequence of scenarios where people continuously enter, move, and exit the scene. We also present a new evaluation matrix comparing the generated scenarios to real-world video in terms of scene level realism, such as density, frequency, coverage, and population similarity, and agent level accuracy, including kinematics, dynamic time warping, diversity, and collision rate. And then we design a runnable framework for this task that replaces the conventional software. Specifically, we designed two models, the crowd emitter and crowd simulator. The crowd simulator and crowd simulator are designed to replace the conventional processes. First, the crowd emitter is designed to replace the conventional populating environment processes, where workers manually paint the populations on the environment. In detail, given an implicit image, a spatial layout prediction module outputs three types of maps. Here, appearance map shows where crowds can enter and exit the scene. Population density map shows where people are likely to gather, and semantic segmentation map represents the scene structure and types of obstacles. Next, we use diffusion models to populate the environment. Crowd emitter diffusion model generates agent parameters including agent type, working pace, entrance time, and the origin and goal coordinates. Here, to model the collectivity, we simultaneously denote all agents in a scene. Through this, we can produce when and where crowds will appear at building entrances or scene boundaries. Second, the crowd simulator is designed to replace the conventional simulating crowds processes, where workers manually draw trajectories on the environment. In detail, we design a trajectory predictor that can generate future paths conditioned on the agent's target behavior state. The behavior state is sampled from Markov chain, where the transition probabilities are dynamically estimated using switching crowd dynamical systems. This enables the trajectory predictor to simulate realistic locomotion with the natural behavior changes such as slow down, turn left, and then accelerate again. This approach is very effective at generating realistic trajectories. Compared to the algorithm-based simple shortest path and diffusion-based noisy and unnatural movements, CrowdES generates continuous and natural actions with smooth behavior transitions over time. Finally, we iteratively generate crowd animations by alternating between the crowd emitter and simulator. By repeating these emission simulation processes, our framework produces continuous crowd behaviors given the environments. We compare our CrowdES framework with two baseline models. The results demonstrate that our framework consistently outperforms these methods across nearly all scene-level realism and agent-level accuracy metrics and datasets. These are visualization of time-varying behavior changes. Web video shows the scene-level behavior changes. Our CrowdES can generate various behaviors from the real world, such as locomotion, leader-follower, group working, and challenging stop and go, stopping to avoid collision, and free pause and work on motions. Right video shows agent-level behavior changes, and I track the man over a 10 minutes period. A man entering the scene, working on the street, talking with a woman, and then moving to other location across the intersection. Next, the woman notices the man, moves away, and returns back. As you can see here, behavior changes are smooth, which was impossible in previous works. And an important thing that we considered is controllability. Our model can automatically generate realistic crowds, but practical applications may need to control it. To do this, we make all the parameters to be controllable. Here, you can change the population size, starting and destination positions, agent types, working pace, and all at once. Lastly, we check the sim-to-real capabilities by training an off-the-shelf trajectory predictor model using synthetic data generated by our framework, and then evaluating real-world data. Compared to the model on the top row, trained on real data, the model in the bottom, trained with synthetic data, could cover a much diverse motions, so shown in yellow lines, and also accurately predict the features such as turning back in the university scene and sharp turning in the Jara scene. We then check the real-to-sim capability in large real-world environment. We capture the 2 kilometers by 1 kilometers area of New York City from Google Maps, covering Central Park and Midtown Manhattan. As you can see, the framework can generate realistic crowd behaviors in such large and complex environments. Thank you for your interest in our work. Please check our project page for more video examples. Also, our codes are available online.